Okay, so our next speaker is Annette Bachmayr from Mainz, and she will speak on different Galois groups of linear differential equations.
Yeah, thank you. I would like to thank the organizers for inviting me here. I'm speaking on this joint project with Michael Wibmer. So in my talk, in the first part, I will introduce this theory of difference, Galois theory of differential equations, and we will have a look at a lot of examples. And then in the second part of my talk, I will show you the main result and say something on the proof. So we start with an example. So this project is on a very specific base field. Oh yeah, maybe? Is this working? No. Yeah? Okay. So we are always working on the base field, that's the field of meromorphic functions over the complex numbers. We differentiate with respect to x. And let's have a look at this equation, where the solution is the exponential of x squared. And so let me first remind you what we would do in classical differential Galois theory. Here we would adjoin the solution to the base field, and that's the Picard-Bessieux extension. And then to define a differential Galois group, you have to look at the automorphisms of this extension that commute with the derivation. Right? And so in this case, this is determined by what it does with y, and since it's a differential automorphism, y needs to be mapped to another solution, so you can only map it to a constant multiple, and in fact, every constant gives rise to such an automorphism, so you get the full GL1. And to be more precise, these are the C rational points of this group, but since C is algebraically closed, and this differential Galois group is a linear algebraic group, these C rational points, they determine the whole group. So G equals GL1 in this example. So same example, same solution, but now in addition, we also look at this endomorphism sigma, that's a shift operator. So a function f of x is mapped to f of x plus 1. And let's look at sigma of y, our solution, that's this function. And if you apply sigma again, we get another function, but what you can see is that we get this relation here. Right, so y and the images under sigma and higher powers of sigma are not algebraically independent. There's a relation, and this difference Galois theory of differential equations sees this equation. By which I mean, so the classical differential Galois theory only sees algebraic relations among the solutions. So if there are lots of relations, the group is small, and if there are no relations, the group is full GLN. And the difference Galois group also sees relations that involve sigmas. Okay, so still the same example. Now the sigma Picard-Bessieux extension is defined as adjoining the solution and also all images under sigma and higher powers. So in this case, we only need to adjoin y and sigma of y. And then the sigma Galois group is defined as, again, let's just have a look at the C rational points here. You define it as the automorphism of the sigma Picard-Bessieux extension that commute with both the derivation and the endomorphism sigma. So again, y needs to be mapped to a constant multiple since it's a differential automorphism. But now, if you apply gamma to this equation, then you get an extra condition, the red one down here, that we didn't have before. So, and then this is the same, then isomorphic to the subgroup of GL1, which with this one condition. However, note that for the complex numbers, this is an empty condition because it's always satisfied, because on the complex numbers, our sigma is the identity. But it's just a very peculiar case because the sigma is trivial on our field of differential constants. So here, these C rational points, they do not contain the information on the whole group. So if you compute the S rational points for some extension S, then you will have the same equation, and then it's not going to be an empty condition. Yeah, so I didn't say what the S rational points are. You also need to consider a group of automorphisms where you extend from the Picard-Vessier ring from C to S. And then the computations are the same, and you get the same condition. So the sigma Galois group is smaller than the classical differential Galois group. Okay, and this theory was established in 2014, a paper by Lucia, Charlotte, and Michael. And yeah, not only over this field, but over all differential difference fields. And basically, you start with a differential equation of order n. Then you need to find a sigma Picard-Vessier extension. So you need to find a complete set of solutions somewhere, and then join the set and also all images under sigma and higher powers of sigma. And you need to do this in a meaningful way, by which I mean you don't want to get new constants. Okay, and by the way, if the field of differential constants is algebraically closed, as it is in our case, then these extensions always exist, but are not unique. And then you can define the sigma Galois group as such an automorphism functor as an example. And that's the subgroup of GLN. And inside GLN, it's given by algebraic equations in the matrix entries and the images of the matrix entries under sigma and higher powers of sigma. So that's what we call a difference algebraic group. Yeah, I would also like to mention that in this theory we have a Galois correspondence and some other results that we also have in classical differential Galois theory. So before we proceed with the differential equations, let's first look at a couple of examples of these groups. So difference algebraic groups, the first example would be linear algebraic groups. So if you have a subgroup of GLN that's given by algebraic equations, then you can view it in particular as something that's given by difference algebraic equations. And then if you have such a linear algebraic group curly G, you can define a subgroup of constant points, which means the matrices where every entry is stable under sigma. So that's something that's not an algebraic group. And in particular, if you have a finite cyclic group, there are two ways to view it as a difference algebraic group. So you can directly view it as a difference algebraic group by just taking the same set of points. Or you can say, in addition, every entry needs to be constant, and it's the constant subgroup. So inside GL1, there's a multiplicative group GM. We have lots of subgroups. So every equation like that defines a difference algebraic subgroup. And similarly for the additive group, every linear difference equation defines a subgroup. So here we also have lots of subgroups. Another example would be the unitary group that's given by this equation. That's also, if you write this as n squared polynomials, this is also a difference algebraic group. So what we're interested in our project was the inverse problem: which difference algebraic groups are sigma Galois groups of some differential equation, or to be more precise, I should say, are sigma Galois groups of some sigma Picard-Vessier extension of some differential equation, because the Picard-Vessier extensions are not unique. yeah, the motivation was, I guess, that there was this paper from 2014, and so the theory was there, but we didn't really have any examples for this theory. So we started with this one case of this very basic field, C of x. Okay, some examples. So we already saw in these slides that this subgroup of GM occurs, right? We had this exponential of x squared, and then we got this group. Also, the constant subgroup of GM does occur. GM, GA, and finite cyclic groups themselves do occur, but no proper subgroups of GA. And also, the constant points of finite cyclic groups, they also do not occur, right? So for GM, some subgroups occur and some do not. Okay, and I would like to explain in the following slides these examples. So let's start with the multiplicative group. If you look at this equation, so we adjoin the exponential function. This satisfies this equation. So sigma of y is e to the x plus 1, which is e times y. And this then has sigma Galois group, the constant subgroup. So why is that? Because let's again just compute the C rational points. If you look at these automorphisms, they are given by the image of y, which has to be constant multiple. But in order to respect that relation, C has to be constant for this C rational points and also for every extension S. So we get the constant subgroup. Now, if we look at this equation where we have the solution e to the x inverse, it's different because here if we consider the images under sigma, we get the exponential of x plus 1 inverse and x plus 2 inverse and so on. And these functions are all algebraically independent by the Cauchy-Ostrowski theorem. So here we do not have any relation among the solutions, so we do not get any constraint on these automorphisms, and therefore we get a full group GM. Okay, so next example would be the finite group of order 2. Consider this example, and the solution is square root of x, and then we get as images square root of x plus 1 and square root of x plus 2 and so on. So there are algebraic relations among these solutions. Everything squared is inside the base field, but other than that, we do not have any relation, by which I mean if you consider this sequence of images, y, sigma squared of y, and so on, then each one of these has still degree 2 over the field where you adjoined all previous ones. And therefore, we get the full finite group of order 2. And maybe this example also explains why you cannot get the constant subgroup of the finite cyclic groups, right? Because you would need to adjoin a function such that in this field extension, where you adjoin this one function which is a square root of something, you also have all the images under sigma. So then if you replace x by x plus 1 in this root function, this would still need to be in your degree 2 extension. And such a thing does not exist. Now let's get back to this slide. So now we did check all subgroup of GM. So let's move on to the additive group. If we want to have the full additive group, we can do the same thing as usual, adjoining a logarithm, because if you look at the images, you have logarithm of x plus 1 and logarithm of x plus 2 and so on, and they are also all algebraically independent. So you have no relations, no constraint on the automorphism group, so you get a full GA. However, for all subgroups, if they're non-trivial, there's no sigma Picard-Vasseur extension. And I would like to explain this to you because the proof is very elementary, but let me first give you a consequence. So then also, if you have a unipotent linear algebraic group curly G, and you consider the constant subgroup, then that is also not a sigma Galois group over the base field. And that's because if you have a unipotent group that has a quotient that's GA, so the constant group then has a quotient that's the constant points of GA, and therefore by the Galois correspondence, if that constant subgroup of GA does not occur, the whole group can also not occur. Okay, so for this claim, let's assume that we do have a Picard-Bessieux extension with a proper subgroup of GA. And we want to show that G is the trivial group. So in the first step, we show that such a sigma Picard-Bessieux extension is always, or can always be obtained by adjoining one antiderivative and its images. And to show this, we use that these sigma Picard-Bessieux rings are torsors under the Galois groups, and then we classified the torsors for subgroups of GA using NH1. So then we got this. Next, since G is a proper subgroup, there has to be some relation. So at a certain point, these elements y, sigma y, and so on have to become algebraically dependent. And then we write this element A that we adjoined an antiderivative of, we call it A, and after subtracting something from y that's a rational function, we can assume that that A is just a logarithmic part, and then, so y is the antiderivative of A, and that means that sigma of y is the antiderivative of sigma of A, and also for higher powers. So we can write that in this form, because sigma is just sending x to x plus 1. And then, since y sigma y to sigma to the n of y are algebraically dependent, the Kolchinov-Strovsky theory gives us a non-zero vector in the complex numbers such that you get a linear combination of these elements that's inside the base field. And now we plug this expression from above in, and then we have that this big term down here has an antiderivative in our base field c of x. And therefore it has to be 0 because it's just a logarithmic part, and it's easy to see that the terms do not cancel unless a is 0, and therefore y is in the base field and g is the trivial group. Now here's another result that says something like negatively, it says like some groups do not occur. This says that if you have a sigma Galois group, then it has to be sigma reduced and sigma connected. The sigma reduced part was known before. It was known that if the sigma on the base field is surjective, which is the case for us, then the group is sigma reduced. And the sigma connected uses the fact that you don't have a finite difference extension of this field. So I don't want to give a definition of these terms. I would rather like to give some examples. So if you have a linear algebraic group, it's always sigma connected. And also all subgroups of the additive groups are sigma connected. But the constant subgroup of a finite cyclic group is not sigma connected. And a subgroup of the additive group that's given by such a linear difference equation is sigma reduced if and only if the constant term A0 is non-zero. So note that there are lots of subgroups of GA that are both sigma connected and sigma reduced. So this means that this criterion is not sufficient, just a necessary criterion. And then our main result says that if you have a linear algebraic group and you consider it as a difference algebraic group, which means you just take the same points, then there exists a sigma Picard-Bessieux extension with that group as Galois group. And in the proof, we use algebraic patching that somehow allows us to boil down this problem from an arbitrary linear algebraic group to 3 cases, namely the additive, the multiplicative group, or a finite cyclic group. And for these 3 cases, we do know how to construct sigma Picard-Vissou extensions, right? We need to join suitable exponential or suitable logarithm or a suitable root, certain root. Okay, so I would like to explain this algebraic patching. So we first just start with fields, so no differentials, no sigmas here. We look at a diamond of fields, which is so we have 4 fields, our base field f, and then which for this particular slide doesn't have to be C of x, but you can think of C of x. So f is contained in 2 overfields f1 and f2, and both of them are contained in another overfield f0. And then we call this a diamond of fields with the factorization property if it satisfies these 2 conditions. So the first is that the intersection of f1 and f2 inside f0 is f. And the second condition is that we have a matrix factorization property. So whenever you have an invertible matrix with entries in f0, you can write that as a product of 2 matrices, one with entries in f1 and one with entries in f2. Okay, an example. So that's a very special condition, but an example of such fields is the following. Now again, f is C of x, so that's the field of meromorphic functions on the whole Riemann sphere. And now we consider 2 open connected subsets, U1 and U2 of the Riemann sphere, such that they cover the whole space and the intersection is connected. And then you let f1 be the field of meromorphic functions on U1, and f2 the field of meromorphic functions on U2, and f0 the field of meromorphic functions on the intersection. And then this quadruple is a diamond with a factorization property over our base field f. And I believe that's a classic result, known like a long time, right? Yeah. And here's an example. So U1 is the blue open disk with radius 2. U2 is the complement of the closed disk with radius 1. And U2 also contains infinity. It's not really seen in this picture. And then U0 is the open annulus. That's connected. So, and the 2 cover the whole space. So if you now consider the field of meromorphic functions f1, f2, f0 on these sets, they are a diamond with the factorization property. Okay, so now, in addition, we look at such diamonds with sigmas and deltas on them. So we start with a group, G. It's generated by 2 closed subgroups, H1 and H2. So 2 groups that are subgroups that are also different algebraic groups. And we consider a diamond with the factorization property, f1, f2, f0, such that all these fields are equipped compatibly with commuting derivations delta and endomorphism sigmas, such that you don't have new constants in f0. And let's assume that we do have sigma Picard-Vissou extensions E1 over f1 and E2 over f2 with groups H1 and H2. Then this patching theorem says, and also that E1 and E2 is contained in f0. And then this statement says that then you can find a Picard-Vissou extension E over your base field f with group G and also contained in f0. So this would be the picture for that. And maybe this sounds familiar to you if you have heard me talk before. That's because this statement is just an adaptation of patching results for other Picard-Vissou theories. Nevertheless, I would like to show you how the proof works, how this factorization property comes in. So in the first step, we just adjust the representations, right? Because this E1 and E2, the Galois groups are just isomorphic to H1 and H2, so they don't sit in the same GLN. And so in the first step, we adjust the representation such that they are both in the same GLN for the same n. And we do that by, again, using that the sigma Picard-Vessier rings are torsors for the sigma Galois groups. And then we showed, I think in another paper, that if you have a subgroup of GLN, then every torsor is isomorphic to a subvariety of GLN. That's not a big thing to prove. So that's the first step. The second step, now we do the matrix factorization, and we consider y1, y2 inverse. So these are in the same GLN, and they are both contained in GLN of F naught, because E1 and E2 are contained in F naught. So we can multiply them there, and then factorize them to get B1 and B2 over F1 and F2, and then B1, Y1 is the same as B2, Y2. That's the same matrix. And this matrix solves the differential equation over our base field F. That's easy to see by the intersection property. So we can adjoin this matrix Y and also the images under sigma and higher powers of sigma, obtain a sigma Picard-Vessier extension, because that's contained in F naught, and F naught didn't have new constants. And we also showed that it has sigma Galois group G. So here it's easy to see that it contains G, because if you base change that E to F1, it has group H1. If you base change it to F2, it has group H2, so it contains both of H1 and H2, so it contains G. And then the intersection property, together with the Galois correspondence, implies that it cannot get bigger. Yeah, so now that we have this statement, we need to know how to generate these groups. We need to go to generating subgroups H, H1, H2, and so on. So, but we are only considering linear algebraic groups. And it is well known that over an algebraically closed field, you can always generate a linear algebraic group by a finite number of GMs, GAs, and finite simple groups. And that doesn't directly imply that you can do the same thing as viewed as a difference algebraic group, because there could be something in between that's not Zariski closed, but it's a difference algebraic group somewhere in between. So it's a stronger statement to say that these groups generated as a difference algebraic group. But here we use that these finitely many subgroups even generated in the following strong sense, that if you consider the multiplication map from the product, that's surjective. Yeah, and in this product, maybe you need to write some of the HIs multiple times, right? But it's still finitely many. And that then implies that also as a difference algebraic group, they do generate it. Okay, so what's the strategy to realize a given G that's generated by finitely many such H1 to HM as a sigma Galois group? In the first step, we choose a suitable diamond of fields with the factorization property. And suitable, in particular, means that we have these endomorphisms on each of them and derivations. And then we need to construct Picard-Vessier extensions E1 over F1, E2 over F2, both contained in F naught with groups H1 and H2. So that's the picture. And then the patching tells you that then there exists a sigma Picard-Vessier extension E over F with group generated by H1 and H2 that's contained in F naught. And then in a second step, we choose a new diamond of fields such that the F naught from the first step is the new F1. So our F1 tilde is F naught. And then, since E is contained in F naught, which is the new F1 tilde, this lifts to a Picard-Vessier extension over F2 tilde with the same group. That's because it's contained in F1 tilde, and F1 tilde and F2 tilde intersect in F, so the group cannot shrink if you lift it to F2 tilde. Okay, and then you need to construct something over F1 tilde with group H3, and then again we apply the patching to obtain something over F that's contained in F0 tilde with group generated by H3 together with the other group that was generated by H1 and H2. And then you continue inductively. So what's left to do is we need to find these suitable diamonds of fields. So we need to find these diamonds that have the factorization property and such that all these fields are equipped with derivations and endomorphisms that extend the one from the base field and that commute and that are compatible with these inclusions in the diamonds, that there are no new differential constants. And the difficult part in this is to find something, to find something that has the sigmas on it. So let's first try the following. Try to find open connected subsets of the Riemann sphere such that they cover the whole sphere and the intersection is connected. Because then, if you consider the field of meromorphic functions on these sets, this is a diamond with a factorization property. You also have differentiations on each of them, no new constants. But how can you get extensions of the sigma shift? So this would need that U1 and U2 are stable and the shift operator sigma. Because then the field of meromorphic functions are also stable. So we first try to do something like this. So it's a shift. So you need to do something that's horizontally invariant. And we consider the blue U1 is the open upper half plane, and the red U2 is some lower open half plane that intersect in this purple stripe. And that's the problem here is that they do not cover P1, right? Because none of them contains infinity, and you can't add infinity to the red or the blue thing because otherwise it wouldn't be open anymore because it doesn't contain a full ball around infinity. Another issue, if you would do this, would be that in the second step, remember that our F0 becomes the F1 tilde. So the thing with the stripe in the middle would be the new U1, and then we would need a new U2 that's connected and together with the stripe covers the whole thing, and that's also a problem, right? Because you can find something connected. And sigma invariant that's going to cover the whole thing. So instead what we do is the following. We consider fields F1 that are union of fields Li, of ascending chains of fields Li, and each of these fields Li is a field of meromorphic function on some open set Vi, and we do this in a way such that these fields Li are not stable under the shift operator, but the union is. So these open subsets Vi are then is a descending chain of open sets. It looks like this. So V1 is the complement of this red closed interval. And V2 is the complement of this interval that's a little bit bigger. And these closed intervals that you cut out get bigger and bigger in every step. And then these L1, L2, L3 is an ascending chain of fields. And you have the shift operator maps this V2 to V1. It's not surjective, but it maps into there. If you shift to the right, you get from V2, you get to V1. And also from V3 to V2, and so on. So we have maps sigma from Vi plus 1 to Vi, and therefore on the level of field of meromorphic functions, we have maps sigma from Li to Li plus 1. So that's our F1. And we do the same thing with F2, only here we cut out an interval, the interval that's translated by I. And then for f naught, we consider the field of meromorphic functions on these intersections. So we cut out both intervals in each step. And again, we have these map sigmas on these fields, so this is also a difference field. And then overall, note that these vi and wi, these are open connected. They cover together the whole Riemann sphere for each I. So in each column, vi and wi together cover the whole sphere, and they have a connected intersection, which is in the third row. So we know that for each I, each column is a diamond with the factorization property. And therefore, also the union is a diamond with the factorization property, because if you take a matrix with entries in f naught, then for some I, this matrix has entries in mi, and you can factor inside this diamond with f, l, I, k, I, mi, and then it gives you a factorization in the union. And similarly for the intersection property. So this is a diamond with the factorization property, and also we have these compatible sigmas, the shift operator on these fields. And again, these are differential fields, no new constants, as we wanted. Okay, so this is a good diamond for the first step. In the second step, remember that we want our f naught to be the new f1 tilde. So this is our f1 tilde. And now as f2 tilde, we just translate this interval one more time to 2i. And then the intersection looks like this. And again, we have a diamond with the factorization property and with shift operator sigma on them. Okay, so now on my last slide, I would like to explain how we then can do what we call the building blocks. So this is our field f1, this is our field f0, that's just copied from the last slide. And now what's left to do is we need to construct a sigma Picard-Vector extension E1 over f1 with group h1 that's contained in f0. And then we will have to do the same thing over f2 and inductively over all other fields that occur. So there are three cases. First case, H1 is the additive group. Then we need to adjoin a suitable logarithm. And this logarithm has to be contained in F0. And it should not be contained in F1 because we want to have the full GA. So we adjoin this logarithm, and I wrote these angle brackets to indicate that we adjoin also sigma of this logarithm and higher powers of sigma. And remember that the logarithm itself is holomorphic on the complex numbers if you subtract this real interval from -infinity to 0. And it's also not meromorphic in infinity. And then this argument 1 over x minus I plus 1 is in that singular locus if and only if x minus I is in a closed interval from -1 to 0. So that's if and only if x is in a translate up to I. So we do see that this function is holomorphic on this open set. It's not meromorphic on this set. So it is contained in M1 and in particular in F0, and therefore also all the images under sigma and higher powers of sigma are contained in F0. Okay. And it has group full GA because it's not a trivial group because it's not contained in F1, and we do know that no other subgroup occurs. And in the second case, we do something similar with an exponential function, and in the third case, we do something similar with a dth root of the same argument, actually. Okay, and then we have all ingredients to puzzle everything together, and that concludes the proof. And thank you for your attention. don't understand. So,
yeah, okay, I will speak it.
yeah.
So, do you have an example where you have a differential equation whose classical Galois group is Unicode and whose sigma Galois group is not the difference group attached to the classical Galois group, where you really have new equation?
You meaning that the group gets smaller? It's not that easy to produce such an example because it's not going to be some. I don't know.
Some work of Galois show that in fact when you have a classical Galois group simple, well, the difference, well, you cannot have anything else than the classical one. So it would be nice to get example of you really have some new equation.
Yeah, but maybe for unipotent groups that might not exist because for G8Z it doesn't.
Yeah.
Then you
if
all.
it exists, should be there.
What do you think? I think maybe.
Yeah, so in fact I also have a question, but it's not for Annette, it's for the audience. So if maybe someone would like to make a conjecture of which groups actually occurs, and so we know a lot of examples occur, we know a lot of examples which don't occur, but we can't really see any systematics behind it. So at least the two of us we couldn't even come up with a conjecture of what should be the answer to the inverse problem. Annette, yeah.
What algorithms in order one?
Algorithm to compute a sigma Galois group of a given differential equation. Is that something?
Yeah, so actually, myself and Carlos, we worked on it and we paused it, but it should be completed eventually. Yeah. Algorithms for order one, yeah, it looks doable. Yeah. Even for order two, it seems reasonable to expect you'd be able to do something.
So this construction works over the complex numbers. Do you have results over the algebraic closure of the rationals? You don't see a way of descending?
No. Are you saying by using these Khrushchevsky arguments or something like that? Yeah.
It's an honest question.
Yeah. No, we don't even started to think about it yet. But yeah.
Yeah, maybe if I could, it's more like a comment. Yes, you would expect that whatever the answer is over the field of complex numbers, you should have the same answer over any algebraically closed field of characteristics 0. But yeah, so in this paper we really crucially need C for this special method in the way we use it. Any other questions? Then let's thank Annette.